This is the next video in a chapter on advanced theories of bonding. We have one type of hybridization left, and that is sp hybridization. So we need to use sp hybridization when we have a central atom that's connected to two electron groups, such as in the molecule CO2. So we know we can draw CO2 like this, with the carbon atom in the center, doubly bonded to an oxygen atom on each side. And our central atom is the carbon. That's the one we're going to need to hybridize in order to correctly predict that 180-degree bond angle. So we need to know the number of electron groups. Carbon has 2 electron groups attached to it. So we'll need to blend 2 atomic orbitals from carbon together in order to hold those. So we'll move down to our orbital section. We're going to write out the valence orbitals belonging to carbon. Carbon has an s valence orbital, and it has 3 p valence orbitals, just like the last time we did it. But we don't need to blend all 4 of them together. We only have 2 electron groups. So we only need to make 2 sigma bonds. We only need to blend 2 orbitals together. And we always choose the s orbital, and then we choose p orbital after we've run out of s. And so these 2 other p orbitals are going to remain unblended. We like them just the way they are. We don't need to make any changes to their shape or energy in order to use them. So we'll push those through the hybridized machine, and from our 2 blended orbitals, we are going to make 2 new sp hybrid orbitals. And from our other 2 p orbitals, they are going to come out looking exactly the same as they went in. So we have 2 new hybrids and 2 atomic orbitals that remain the same. And these sp hybrid orbitals are going to be 50% s character and 50% p character. So this is the most s-rich orbital, s-rich hybrid orbital, other than the s orbital itself, that we've seen. So if you're drawing an accurate shape, this is going to be the most spherical looking of all 3 of the hybrids we've seen so far. So moving into the shape, we are going to mix together 2 atomic orbitals, 1 s orbital and 1 p orbital. Hybridize those. And we will get a similar dopey looking uneven hybrid orbital, this one with 1 lobe even more large than the other. And we can just go ahead and draw this one on the axis because we're going to get a 180-degree angle out of this. There's one, and there is our other sp hybrid orbital. And we can draw them together on the same shape, larger lobes only, like this. And again, this looks like a drawing of a single p orbital, but it's really a lazy man's drawing of 2 sp orbitals on the same central atom. We've just left the smaller lobes out. And these new hybrid orbitals sit at a 180-degree angle to each other, which is a perfect model for our linear VSEPR geometry. So that's great. We're super happy with that. Now let's find out if these 2 hybrid orbitals have the same energy. So we'll start out with our 3 2p orbitals and our 1 2s orbitals for carbon. We're only going to blend 2 of them together, only 1 s and 1 p. And then our other 2 p orbitals are going to remain unblended. They're fine. We're happy with their energy. Put them through the hybridized machine. We always include our energy axis with a label. So here's where our 2p energy was. Here's where our 2s energy was, and we are going to be exactly 50-50, so halfway in between those two original energies is going to be the energy for our resulting sp orbitals. And then we'll have 2 of those 2p orbitals at the same energy as they were before. 2 hybrids with intermediate identical energies are produced. Awesome. So now if we use those orbitals that we've made to do sigma overlap in our CO2 molecule, we're going to choose an sp orbital for each of the carbons. So we'll reproduce this shape, our lazy shape, that only has the larger lobes shown. Carbon sp hybrid orbitals. And then each of our oxygens are going to choose their half-filled valence orbital, which is going to be a 2p orbital. And so between each set of oxygen 2p and carbon sp, we are going to form an excellent overlap sigma bond. Those are our 3 types of bonding: sp3, sp2, and sp. So let's take a second to summarize what we've learned about hybridization and make a table and talk about how similar and different the types of hybridization are. So in our updated valence bond theory, we added a couple of new shapes to our shapes of orbitals. We now have 5 orbitals that have s and or p quality. So we'll rank them from how much they're like s to how much they're like p. So we'll have the s orbital on one end, we'll have the p orbital at the other end, and then our 3 hybrid orbitals will go from left to right in order of the most s quality they have. So our sp orbital was 50% s. So one of these lobes is going to be way bigger than the other one. sp2 is only 33% s. So the difference in size of the orbitals is going to be a little bit less. I'm not even sure if you can tell from that picture. And our sp3 orbital is 25% s. So those lobes are now almost the same size. So hopefully that's a little bit more clear that as we move from sp to sp2 to sp3, those lobes are getting more and more similar in size as we decrease in s character. That's important. Let's write that down. So the sp is most similar to an s orbital, and our sp3 hybrid is most similar to a p orbital. And now let's make a table of the geometries. Help you out when you are trying to identify hybridization out in the wild. So this table is going to have the electron groups, number of electron groups, then it's going to have the name for the electron geometry, and then the hybridization that we just learned about. And then I'll give you some example situations where you might see these. We'll make this a big table. There's going to be a lot of stuff in it. There we are. And we'll wait for the doc-chem to come back into focus. There we are. So let's start small. The fewest number of electron groups a central atom can have is 2. We know that electron geometry is called linear. And if you mix 2 orbitals together, you are going to end up with an sp hybridization situation. And you might see this for carbon or for nitrogen, something where you have a central atom that is bonded to 2 things. See, these are the sorts of situations that you might see. If we have 3 electron groups, this is called trigonal planar. And if we mix 3 atomic orbitals together, we will make Sp2 hybrid orbitals. You might see this in a situation where you have a carbon or a nitrogen atom that is bonded to 3 electron groups. If it's carbon, usually these are all atoms. If it's nitrogen, usually 2 of these are atoms and 1 is a lone pair. If we have 4 electron groups, the electron geometry is called tetrahedral. We mix 4 atomic orbitals together to get Sp3 hybrid orbitals. And so we might see a carbon, a nitrogen, or an oxygen with 4 electron groups. Carbon isn't the only thing that can be hybridized. When we see carbon, it usually has 4 bonding groups. When we see nitrogen, it usually has 3 bonding groups and 1 lone pair. And when we see oxygen, it usually has 2 bonding groups and 2 lone pairs in order to complete its octet. So you might be able to recognize these when you see them in the wild. Now, these are the only types of hybridization that we've gone into great detail for. We can continue and use hybridization to explain our 5 and 6 membered electron geometry, but we're going to have to bring in the d orbitals. So if we want to explain our 5-membered electron geometry, called trigonal bipyramidal, we're going to need a 5th atomic orbital in the valence shell, and so we need to pull in the d orbital in that shell. And we can use that to explain things such as a phosphorus. That's an example of an atom that might be seen taking 5 bonds. And if we're trying to explain a 6-membered electron geometry, which we call octahedral, we need to pull in 2 of the valence d orbitals, giving us a hybridization called Sp3d2. And you might see that in an atom such as sulfur, which is large enough to hold 6 bonds. Now, we didn't go into great detail on these last 2 d orbital involved hybridizations in our previous videos because these are not really excellent models of explaining how this geometry works. But you might see it in some of your other textbooks, and it's important for you to have heard of this before. So these models for 5 and 6 member geometries are not really great models. The d orbitals technically have too high of an energy to be able to blend with the s and p, so it's pretty unlikely that this would actually happen. The d orbitals in main group elements are too high energy to blend with the s and p orbitals in that same shell. So it's an okay approximation just to give us the geometry, but it's not a very useful explanation in general. But when it's time to move on to the next advanced bonding theory, the next theory is going to do a much better job at explaining these types in 5 and 6 member geometry. So hang tight. I promise that a better explanation is coming your way. So in the next video, we will move on to valence bond theory and multiple bonds.